The distance between stars is a measurable physical reality defined by motion, light, and geometry, not by how close or far stars appear in the sky. From Earth, stars seem scattered across a flat dome, but each one occupies a precise position in space, separated from others by distances that can be described, calculated, and compared using consistent physical rules. Understanding these distances begins with recognizing that space itself is vast, structured, and mostly empty, and that the separations between stars are a normal feature of how matter is distributed in the universe. Welcome to AstraFlow. Here, science drifts quietly, and understanding comes without effort. If you'd like, you can share a thought in the comments or quietly subscribe for future journeys like this. Now, let's begin. When we look up at the night sky, our eyes receive points of light that seem equally distant, as if placed on the inside of a sphere surrounding Earth. This impression is a result of how human vision works and how little depth information we receive from very distant objects. In reality, each star is located at a specific distance from us and from every other star, forming a three-dimensional arrangement that extends in all directions. The science of stellar distance starts by moving away from visual appearance and toward measurement. Astronomers define distance in space by observing how objects behave over time and how light travels between them. Light does not arrive instantaneously. It moves at a fixed speed through empty space, and that speed becomes a reliable ruler. When we say a star is far away, we mean that light has taken a long time to travel from that star to Earth. Distance, in this sense, is not abstract. It is directly tied to physical travel time and to predictable laws of motion. The nearest star to Earth is the Sun. Its distance is close enough that we measure it in terms of the average separation between Earth and the Sun itself. This baseline distance is called an astronomical unit. It provides a reference point that helps us describe larger separations. Once we step beyond the Sun, however, distances increase so quickly that new units become necessary. Stars outside our solar system are so far away that astronomical units become unwieldy, and larger scales are required to maintain clarity. One of these larger units is the light year. A light year is the distance light travels in 1 year as it moves through space. This is not a measure of time in the usual sense, but a measure of length. When we say a star is 4 light years away, we are saying that the light we see tonight left that star 4 years ago and has been travelling ever since. This relationship between distance and light travel time is central to how astronomers map the positions of stars. It's important to note that stars are not arranged with any intention of even spacing. Their distances from one another are the result of how gas clouds collapsed, how gravity shaped regions of space, and how stars moved over long periods of time. Some stars happen to be relatively close neighbours, while others are separated by enormous gaps of empty space. There is no standard distance between stars. Instead, there is a range of separation shaped by physical processes. Within our local region of the galaxy, stars are typically separated by several light years. This means that if one were to travel from one star to the next at the speed of the fastest human-made spacecraft, the journey would still take tens of thousands of years. This fact is not emphasized to create a sense of impossibility, but to ground our understanding of scale. Stellar distances are large because the universe itself is large, and because matter occupies only a small fraction of the available volume. Despite these vast separations, stars can appear close together in the sky. This is because distance along our line of sight is not easily perceived. 2 stars may lie in nearly the same direction from Earth, while being separated by many light years in depth. This effect is similar to seeing 2 distant mountains align visually, even though one is far beyond the other. In astronomy, this distinction between apparent proximity and actual distance is fundamental. To overcome this limitation, astronomers rely on motion. As Earth orbits the Sun, our position in space changes slightly over the course of a year. nearby stars appear to shift their position against the background of more distant stars. This small apparent shift is known as parallax. By measuring how much a star appears to move and knowing the size of Earth's orbit, astronomers can calculate the star's distance using geometry. This method works reliably for stars within a few thousand light-years of Earth. Parallax demonstrates an important principle. Distance in space is not inferred by brightness alone. A star may appear bright because it is close, or because it is intrinsically luminous, or both. Without measuring distance directly, appearance can be misleading. The science of stellar distance separates observation from interpretation, relying on repeated measurements and physical models rather than intuition. As distance increases, direct parallax measurements become more difficult. The shifts become smaller and harder to detect. For more distant stars, astronomers use additional methods that build upon known physical properties of stars. By understanding how stars produce light and how that light changes with distance, astronomers can estimate how far away a star must be to appear as it does. These methods are calibrated carefully and cross-checked to maintain accuracy. Throughout this process, one idea remains constant. Space between stars is not filled with obstacles or structures that define distance. It is mostly empty. The distances we describe are lengths through near vacuum, shaped only by gravity, radiation, and the slow motion of matter. This emptiness is not unusual or rare. It is the normal condition of the universe. From a calm observational standpoint, the distance between stars is simply the result of how the universe expanded, cooled, and organized itself over billions of years. Stars formed where matter gathered, not everywhere at once. The gaps between them reflect where matter did not collect. These gaps are stable, measurable, and persistent over long periods of time. As we begin this exploration, there is no need to hold all these scales in mind at once. Understanding builds gradually, layer by layer, starting with nearby space and expanding outward. Each distance we describe connects smoothly to the next, forming a continuous structure rather than a set of isolated facts. For now, it is enough to rest in the idea that stars are not scattered randomly across a surface, but arranged throughout a deep, three-dimensional space. The distances between them are large, but they follow consistent physical rules. These rules allow us to measure, compare, and map the stars with clarity and patience. To understand stellar distance more clearly, it helps to begin with the region of space closest to us, often called our immediate stellar neighbourhood. This is the small volume of the galaxy that surrounds the Sun, containing the stars that are nearest in physical distance, not just in appearance. Within this neighbourhood, distances are still large by everyday standards, but they are small enough to be measured with the most direct and reliable methods available. The closest star system to the Sun, beyond the Sun itself, lies a little over 4 light-years away. This means that light leaving that system takes more than 4 years to reach Earth. Even at this nearest scale, the separation is already far beyond anything encountered in human experience. There are no stars between the Sun and this neighbour. The space in between is mostly empty, containing only sparse gas, dust, and low levels of radiation. Several other nearby stars occupy this same local region, each separated from the Sun and from one another by a few additional light-years. Together they form a loose collection known as the local stellar neighbourhood. This is not a cluster in the sense of stars bound tightly together by gravity. Instead, it is simply a region where stars happen to be passing through the same part of the galaxy at roughly the same time. Within this neighbourhood, stars are distributed unevenly. Some are slightly closer together, while others are more isolated. The typical distance from one star to its nearest neighbour in this region is several light-years. This spacing arises naturally from how stars form inside large clouds of gas. When these clouds collapse, they fragment into many stars, but the fragments are separated by enough distance that each star evolves largely on its own. These separations remain relatively stable over long periods. Stars move through space, orbiting the centre of the galaxy, but their speeds are modest compared to the vast distances involved. Over thousands of years, the positions of nearby stars change only slightly. Over millions of years, the pattern slowly shifts, but the overall spacing remains similar. One useful way to think about this neighbourhood is as a low-density environment. Even though stars are massive and luminous, they occupy very little volume. If the Sun were reduced to the size of a grain of sand, the nearest star on the same scale would be several kilometres away. This comparison is not meant to dramatise distance, but to provide a stable reference for how empty interstellar space truly is. Despite this emptiness, nearby stars influence each other through gravity in subtle ways. Over long timescales, their motions are affected by the combined gravitational field of the galaxy. However, at the scale of individual stellar separations, these interactions are weak. Each star follows its own path, shaped more by the galaxy as a whole than by its immediate neighbours. Observationally, nearby stars offer an important advantage. Because they are close, their distances can be measured accurately using parallax. This allows astronomers to build a reliable map of the local stellar neighbourhood. These measurements form the foundation for understanding larger distances farther out, since they provide well-calibrated reference points. When astronomers chart these nearby stars, they find no sharp boundaries marking where the neighbourhood ends. Distance increases gradually. The concept of nearby is defined by measurement precision, rather than by a physical edge. As instruments improve, the neighbourhood expands smoothly outward. For someone observing the night sky, many of these nearby stars are not visually remarkable. Some are faint, others are bright, but brightness alone does not indicate proximity. Several nearby stars are dim because they are small or cool, while some distant stars appear bright because they are large or highly luminous. Distance must be determined independently of appearance. This local region of space serves as a calm starting point for understanding stellar distances. It is close enough to be measured directly, yet distant enough to demonstrate how quickly space opens up beyond the solar system. By becoming familiar with this neighbourhood, it becomes easier to accept larger scales without strain. As this idea settles, there is no need to imagine movement or travel. The focus remains on position and separation. Stars exist where they are, held in place by predictable motions and long-term stability. The distances between them are not changing rapidly. They are part of a slow, steady structure. From here, the exploration can extend outward step by step, using this nearby region as a reference. The same principles apply at larger scales, only the numbers change. For now, attention rests on the simple fact that even the closest stars are separated by vast, quiet distances, forming a spacious and orderly environment around the Sun. As distances between stars increase beyond the immediate neighbourhood of the Sun, the way we describe those distances becomes just as important as the distances themselves. Ordinary units used in daily life, such as meters or kilometres, are well suited for measuring roads, cities, and even the size of planets, but they become impractical when applied to the space between stars. The numbers grow so large that they lose clarity, making comparison and understanding more difficult than necessary. To maintain precision and calm consistency, astronomers use units designed specifically for space. The first of these is the astronomical unit, often abbreviated as AU. One astronomical unit is defined as the average distance between Earth and the Sun. This distance is measured precisely using radar signals and orbital dynamics, making it a stable and well-known reference. Within the solar system, astronomical units provide a clear way to describe planetary orbits and relative spacing. However, once we move beyond the solar system, astronomical units quickly become cumbersome. The nearest star lies more than 200,000 astronomical units away. expressing distances in such large numbers offers little intuitive advantage and makes it harder to see relationships between different stars. This limitation leads naturally to the use of larger, more suitable units. The most commonly used unit for interstellar distance is the light year. A light year is defined as the distance light travels in 1 year through empty space. Light moves at a constant speed, approximately 300,000 kilometers per second. Over the course of a year, this adds up to a distance of nearly 10 trillion kilometers. By using the light year, astronomers tie distance directly to a fundamental physical constant, rather than to human-scale measures. It is important to understand that the term light year refers to distance, not to time itself. The year in the name describes the duration of light's travel, not the age of the object being observed. When a star is said to be 10 light-years away, this means its light has been travelling for 10 years before reaching Earth. The distance and the travel time are directly linked, but they are not interchangeable concepts. In some contexts, astronomers also use the parsec, another unit of distance. A parsec is defined based on parallax geometry, specifically the distance at which a star would show a parallax shift of 1 arc-second as Earth orbits the Sun. 1 parsec is equal to about 3.26 light-years. While the term may sound technical, it provides a convenient way to connect measurement technique and distance in a single unit. Parsecs are especially useful when discussing large-scale structures such as star clusters and galaxies. Because many astronomical equations are simpler when written in parsecs, this unit is commonly used in scientific literature. For general understanding, however, light-years remain more familiar and easier to visualize in relation to light travel. These units allow astronomers to describe distance without constantly converting between extremely large numbers. More importantly, they allow distances to be compared smoothly across different regions of space. When two stars are said to be 5 and 10 light-years away, the relationship between those distances is immediately clear. Using these units also helps maintain consistency when discussing how stars are arranged. The distances between stars within a cluster, across a galaxy, or between galaxies can all be expressed using the same basic framework. The scale changes, but the underlying unit remains stable. From an observational perspective, these distance units do not imply motion or effort. They are descriptive tools. They allow astronomers to say where things are without suggesting travel, journey, or difficulty. This keeps the focus on structure rather than on experience. As this framework settles in, it becomes easier to listen to numbers without strain. A few light years, tens of light years, hundreds, or thousands all fit within the same conceptual space. The mind does not need to picture the entire distance. It only needs to recognize that the unit remains consistent. With these measurement tools in place, the distances between stars become orderly rather than overwhelming. Each number refers to a defined length, grounded in the behavior of light and motion. This provides a steady foundation for understanding how stars are spaced throughout the galaxy and beyond. Once distance units are established, the role of light becomes central to understanding how those distances are known. Light is not only what allows stars to be seen, but also what allows their positions to be measured. Every observation of a star is an observation of light that has travelled through space for a specific length of time. The travel time carries direct information about distance. Light moves through empty space at a constant speed. This speed does not depend on the motion of the source or the observer. Because of this, light provides a stable reference that can be used across the universe. When astronomers measure distance using light, they are relying on a property of nature that remains the same everywhere. When a star emits light, that light spreads outward in all directions. As it travels, it does not weaken because of resistance or friction. Instead, it spreads over a larger area, becoming less concentrated with distance. This spreading affects how bright the star appears when the light finally reaches Earth. By understanding how light behaves as it travels, astronomers can relate brightness to distance. Once the star's intrinsic properties are known, time enters this process naturally. Because light takes time to move from one place to another, observing a distant star means observing light that left the star in the past. The farther away the star is, the older the light we receive. This does not change the star's current position, but it does affect how we receive information about it. This relationship between distance and time does not introduce uncertainty. Instead, it provides clarity. Light travel time is predictable and measurable. When astronomers say a star is 100 light-years away, they are describing both the distance and the time it takes for light to cross that distance. The two are linked through a constant speed. Light also carries detailed information. Its colour, spectrum and intensity all change in measurable ways depending on the conditions at the source and the distance travelled. By analysing starlight, astronomers can determine temperature, composition and motion alongside distance. Distance measurement is therefore integrated into a broader process of observation. One common method relies on standard candles, objects whose intrinsic brightness is known. If two stars produce the same amount of light but one appears dimmer, the dimmer one must be farther away. This method depends on careful calibration and comparison with nearby stars whose distances are already known through parallax. At all stages, light remains the connecting element. It links the physical location of a star to the instruments on Earth. There is no direct contact, only continuous reception of information carried by photons across empty space. Importantly, light does not compress or distort distance, it simply reports it. The delay we observe is not an illusion or an effect of perspective, it is a direct consequence of finite speed. This makes light a trustworthy messenger. As these ideas settle, distance becomes something that unfolds gently rather than abruptly. Each additional light year adds a predictable amount of travel time. There are no sudden jumps or hidden shortcuts. Space extends smoothly, and light moves through it steadily. This steady behaviour allows astronomers to build layered maps of space, starting with nearby stars and extending outward. Each layer relies on the same principles, only applied at greater scale. The role of light remains unchanged throughout. With this understanding, it becomes easier to accept that looking far into space is also looking back in time, without attaching significance beyond measurement. It is simply how information travels. The idea can rest here, complete in itself. Distance is measured through light's journey, and light follows clear, stable rules as it moves between stars. When stars appear close together in the night sky, that closeness is often the result of alignment rather than true proximity. From Earth, the sky presents itself as a two-dimensional surface, and our eyes naturally interpret patterns based on position rather than depth. This makes it easy to assume that stars near each other visually are also near each other in space. In reality, stars that seem adjacent may be separated by dozens, hundreds, or even thousands of light years. This effect arises because distance along the line of sight is difficult to perceive without motion or reference points. On Earth, depth perception relies on binocular vision, shadows, and known object sizes. None of these cues function effectively at astronomical distances. As a result, stars collapse visually into a flat arrangement, even though they occupy a deep layered structure. Constellations provide a familiar example of this phenomenon. The stars that form recognizable shapes in the sky are often unrelated physically. They lie at very different distances from Earth, but happen to align in a way that creates a pattern from our viewpoint. These patterns are culturally meaningful but scientifically coincidental. They do not represent physical groupings of stars. This visual compression does not interfere with measurement. Astronomers account for it by separating angular position from distance. Angular position describes where a star appears on the sky's surface, while distance describes how far away it truly is. Both quantities are measured independently using different techniques. The separation of these two ideas allows for precise mapping. A star's position on the sky tells us its direction. Its distance tells us how far along that direction it lies. Together, these values define a three-dimensional location. This approach removes ambiguity and allows stars to be placed accurately in space. The difference between appearance and reality becomes especially clear when stars are observed over time. As Earth moves around the Sun, nearby stars shift slightly against the background of distant stars. This motion reveals depth that is otherwise invisible. Stars that are close show noticeable shifts. Distant stars remain nearly fixed. This layered structure means that the sky is not a boundary, but a window. Light arrives from many distances at once, overlapping in our view. The eye does not separate these layers, but instruments and measurements do. The result is a calm separation between what is seen and what is known. Understanding this distinction helps stabilize the concept of stellar distance. It removes the need to imagine stars as clustered or crowded based on appearance alone. Instead, each star is allowed its own position, independent of how it aligns with others in our view. This principle also explains why star charts change very little over human lifetimes. Even though stars are moving through space, their distances are so great that changes in alignment occur slowly. The sky appears stable, because the scales involved are large and the motions are gradual. As this idea settles, the sky can be observed without expectation of closeness or grouping. Visual patterns remain useful for orientation, but distance remains a separate measured property. The stars continue to appear calm and evenly scattered, while their true separations extend quietly into depth. The night sky gains depth when distance is considered as a separate dimension rather than an implied feature of appearance. Depth in astronomy refers to how stars are distributed along the line extending outward from Earth, away from the observer. This dimension is not directly visible, but it is measurable and consistent. Once depth is acknowledged, the sky becomes a volume rather than a surface. Every direction we look contains stars at many different distances. Some are relatively near, measured in a few light years. Others lie hundreds or thousands of light years away. Even though they may appear equally sharp to the eye, the clarity of a star's point of light does not reveal how far it has travelled. Only careful measurement can do that. This layered structure means that space is filled unevenly. There are regions with slightly higher concentrations of stars and regions with fewer. These variations are subtle at the scale of naked eye observation, but they become clear when distances are plotted. The result is not a shell of stars around Earth, but a deep field extending in all directions. Astronomers describe this depth using 3 coordinates. 2 define direction across the sky, and 1 defines distance outward. This system allows each star to be placed in a stable spatial context. Once placed, its relationship to other stars becomes clear. Stars that appear close may be far apart in depth, while stars far apart visually may be near neighbours in space. The concept of depth also explains why some stars are affected more strongly by interstellar material. Dust and gas between stars can absorb or scatter light. Stars that lie deeper along a line of sight may appear dimmer or reddened, not because they are intrinsically faint, but because their light has passed through more material. This effect depends on distance, not direction. Depth becomes especially important when studying large structures such as spiral arms within the galaxy. Stars that seem to form a continuous band across the sky may belong to different arms at different distances. Without depth measurements, these structures would remain indistinct. With them, patterns emerge calmly and reliably. This understanding does not require imagining motion or travel. It is a static description of position. Stars occupy space in a way that is stable over long timescales. Their depth relative to Earth changes slowly, governed by predictable motion through the galaxy. As the idea settles, the sky can be thought of as transparent rather than flat. Light passes through layers of space before reaching the observer. Each star contributes a single point of light. but that point carries information about how deep into space it originated. There is no need to visualize the entire depth at once. It is enough to recognize that every direction contains distance, and that distance is measured, not inferred. This recognition quietly reshapes how the sky is understood. Depth adds order without complexity. It allows stars to be placed without crowding, each one separated by space that remains mostly empty. The sky remains calm, even as it becomes three-dimensional. One of the most direct ways astronomers measure the distance to nearby stars relies on a simple geometric effect called parallax. Parallax is the apparent shift in position of an object when viewed from two different locations. In everyday life, this effect can be noticed by holding a finger in front of your face and alternating which eye is open. The finger seems to move relative to the background even though it remains still. In astronomy, the same principle applies, but on a much larger and slower scale. For stellar parallax, the two observation points are provided by Earth's orbit around the Sun. As Earth moves from one side of its orbit to the other, over the course of a year, our viewing position in space changes by a known amount. Nearby stars appear to shift slightly against the background of much more distant stars. This shift is extremely small, but it is measurable with precise instruments. The amount of this apparent shift depends directly on distance. A nearby star shows a larger parallax shift than a distant one. If a star is very far away, its shift becomes so small that it is nearly indistinguishable from zero. This relationship allows distance to be calculated using straightforward geometry. Once the size of Earth's orbit is known, the measurement itself does not require interpretation or modelling of the star's properties. It relies only on position and angle. This makes parallax one of the most reliable distance measurements in astronomy. It serves as a foundation upon which other methods are built. Distances measured by parallax are often used to calibrate more indirect techniques that apply to stars farther away. Because the shifts involved are so small, parallax measurements demand patience and stability. Even the closest stars shift by less than 1 arcsecond, an angle smaller than can be resolved by the human eye. Early astronomers suspected parallax existed long before they could measure it, but their instruments lacked the necessary precision. Only with improved telescopes and careful observation did parallax become a practical tool. Modern space-based observatories have refined this method significantly. By operating above Earth's atmosphere, they avoid distortions that blur measurements from the ground. As a result, parallax distances are now known for millions of stars, creating a detailed three-dimensional map of our region of the galaxy. The value of parallax lies not only in the distances it provides, but in the clarity it brings to scale. When a star's distance is known through parallax, its true brightness can be calculated. This reveals whether the star appears bright because it is close, or because it is inherently luminous. In this way, distance separates appearance from physical reality. Parallax also confirms that space is not arranged symmetrically around Earth. Stars do not lie on a sphere at equal distances. Instead, they form an uneven distribution that extends outward in all directions. The gradual decrease in parallax shift with distance reflects this continuous depth. There are limits to the method. Beyond a certain distance, parallax shifts become too small to measure accurately, even with advanced instruments. At that point, astronomers turn to other techniques that depend on calibrated brightness or spectral features. These methods are anchored by parallax measurements at closer ranges, ensuring consistency. As an idea, parallax is stable and self-contained. It does not require imagining travel, speed, or effort. It simply compares positions taken at different times. The star remains still. Earth moves. The geometry does the rest. This calm reliance on geometry underscores a broader theme in astronomy. Distance is not guessed or felt. It is measured through repeated observation and careful reference. Parallax embodies this approach in its simplest form. Once understood, Parallax allows nearby space to feel structured and dependable. Distances are not vague. They are the result of angles and baselines quietly revealing how stars are arranged around us. The concept can settle here, complete on its own. Distance emerges from motion and perspective, not from appearance. The nearby stars take their places in space, defined by small, steady shifts observed over time. Human perception evolved to function within a narrow range of distances shaped by the needs of movement, coordination, and survival on Earth. Within this range, depth is sensed through familiar cues such as overlap, motion, and relative size. These cues work well for nearby objects, but they lose effectiveness as distance increases. At astronomical scales, they disappear entirely. This limitation is not a flaw, but a natural boundary of biological perception. When we look at stars, the light entering our eyes carries no built-in indicator of distance. A nearby star and a distant star can appear equally sharp, equally steady, and equally present. The eye receives both as points of light, and without reference points or motion, it has no way to separate them in depth. The result is a sky that appears evenly spaced even though it is not. This limitation explains why stellar distance remained unknown for most of human history. Early observers could track patterns, cycles, and motions, but not depth. The stars were mapped in 2 dimensions, and this flat representation was sufficient for navigation and timekeeping. Distance was not required for those purposes, and so it remained outside practical concern. The shift toward understanding stellar distance began when observation moved beyond unaided vision. Instruments introduced precision, repeatability, and sensitivity to small changes. Telescopes did not immediately reveal distance, but they allowed stars to be measured more accurately. Over time, this accuracy made subtle effects, such as parallax, detectable. Even with instruments, interpreting distance requires abandoning intuitive judgment. A bright star is not assumed to be close. A faint star is not assumed to be distant. Instead, brightness becomes one piece of information among many. Distance is determined through measurement, not impression. This separation between perception and measurement is a stable feature of astronomy. It does not introduce uncertainty. It removes it. By relying on repeatable physical effects rather than subjective appearance, astronomers avoid systematic error. The sky becomes something that is measured rather than interpreted. The limits of perception also influence how distance is communicated. Large numbers can feel abstract when they fall outside everyday experience. This does not mean they are less real. It simply means they require a different form of understanding. Astronomical distance is accepted through consistency and comparison, rather than visualization. For example, knowing that stars are typically separated by several light years does not require imagining the full span of that distance. It is enough to know that the same unit applies everywhere, and that relative spacing can be compared reliably. One star may be twice as far as another, or 10 times as far. These relationships are meaningful even without a mental image. This approach mirrors how other scientific quantities are understood. Few people visualize an electric field or a magnetic force directly. Instead, they understand how these quantities behave and how they are measured. Stellar distance fits into this same category. It is known through behavior, not appearance. Accepting the limits of perception also prevents confusion when scales change. As distance increases, the same principles apply. Light still travels at the same speed. Parallax still decreases predictably. Brightness still follows known laws. The mind does not need to adapt to new rules, only to new magnitudes. This stability allows understanding to remain calm. There is no need to adjust expectations or search for new intuition. The same framework extends outward, layer by layer. Distance grows, but the method remains unchanged. From this perspective, the difficulty in imagining stellar distance is not an obstacle. It is simply an indicator that the universe operates beyond the scale of human sensation. Measurement bridges that gap quietly and effectively. As this idea settles, the stars can be observed without trying to assign closeness or familiarity. They remain points of light, while their true positions are held by numbers, relationships, and geometry. The division between seeing and knowing becomes clear and untroubled. This understanding prepares the ground for moving outward, beyond nearby space, without strain. Distance becomes something accepted rather than pictured. The structure of space remains consistent, even as the scale expands. Beyond the immediate neighbourhood of the Sun, the distances between stars begin to reflect the larger structure of the galaxy we inhabit. This structure is known as the Milky Way, a vast, rotating system containing hundreds of billions of stars. Within this system, stars are not distributed evenly, but they are also not tightly packed. Their spacing follows patterns shaped by gravity, motion, and the history of star formation. Inside the Milky Way, stars are organised into regions such as the central bulge, the disk, and the spiral arms. Our Sun lies within the disk, in a region where stars orbit the galactic centre in broadly similar paths, even here where stars are more numerous than in intergalactic space. The average distance between individual stars remains large. Typical separations are measured in light years, not in fractions of a light year. Within the spiral arms, stars tend to be slightly closer together than in the regions between arms. This is because spiral arms are sites where gas and dust are more concentrated, leading to more frequent star formation. Even so, the increased density is modest. Stars are still separated by large volumes of empty space. The arms appear dense only when viewed on galactic scales. The disk of the galaxy has a thickness of several thousand light-years, and stars are distributed throughout this depth. When we observe stars in the plane of the galaxy, we are looking along a crowded line of sight that extends across great distances. Many stars appear in similar directions, but they lie at very different depths. Distance measurements are what allow these layers to be disentangled. As distance increases within the galaxy, direct parallax becomes less effective, and other methods are used. These methods rely on comparing intrinsic stellar properties with observed light. Because the structure of the galaxy is relatively stable, patterns in stellar populations can be used to estimate distance with reasonable confidence. These estimates are refined continually as more data becomes available. Within this framework, the Milky Way is not experienced as a single object, but as a gradual increase in scale. Nearby stars transition into more distant ones without a clear boundary. The distances between stars increase smoothly, maintaining the same basic spacing relationships even as the total volume grows. The fact that stars remain widely separated even within a galaxy helps explain why stellar collisions are extremely rare. Although the galaxy contains vast numbers of stars, the empty space between them dominates. Each star follows its orbit largely unaffected by close encounters, contributing to the long-term stability of the system. This stability allows astronomers to model the galaxy's structure using average distances and motions. Individual stars may drift over millions of years, but the overall pattern persists. Distances within the Milky Way can therefore be discussed calmly, as part of a steady rotating system rather than a chaotic swarm. As this idea settles, the scale of the galaxy becomes easier to hold. It is not necessary to imagine every star at once. It is enough to recognize that stars are distributed through a large volume, separated by consistent gaps, and organized by long-term gravitational patterns. The distances within the Milky Way are large, but they follow rules already established. The same concepts used for nearby stars extend outward smoothly. Space remains mostly empty. Measurement remains reliable. The galaxy becomes a structured environment rather than an overwhelming one. From here, attention can continue outward, or pause briefly within this galactic setting, allowing the idea of stellar spacing to remain stable before expanding further. Even within regions of the galaxy that contain many stars, the dominant feature of space is emptiness. The distances between stars are far greater than the sizes of the stars themselves, and this ratio remains consistent across most environments. Understanding this sparsity helps clarify why stellar systems remain stable over long periods and why space behaves as it does. A typical star, like the Sun, has a diameter of about 1.5 million kilometers. By contrast, the distance to the nearest neighboring star is measured in trillions of kilometers. When these scales are compared, the star occupies an almost negligible fraction of the surrounding space. This imbalance between size and separation defines the structure of stellar environments. Even in denser regions, such as star clusters, stars rarely approach one another closely. Clusters may contain thousands of stars within a relatively small volume, but small in this context still means light years across. The average separation remains large enough that gravitational interactions between individual stars are weak, except over very long timescales. This sparsity means that most of the space between stars is filled with low-density gas, dust, and radiation. These components play important roles in star formation and galactic evolution, but they do not significantly reduce the distances involved. Space remains largely transparent and unobstructed. When astronomers describe star density, they often do so in terms of average spacing rather than crowding. This approach emphasizes separation rather than accumulation. A region with higher density simply means that stars are somewhat closer together on average, not that space is filled with objects. The empty nature of space also explains why galaxies can pass through one another with little direct interaction between stars. When galaxies merge, their stars mostly continue along new orbits without colliding. The distances between stars are so large that direct contact is extremely unlikely, even during such dramatic events. For observation, this emptiness provides clarity. Light travels vast distances without being significantly scattered or absorbed. This allows distant stars to be observed with precision. The lack of obstacles preserves information over long spans of space. From a measurement standpoint, empty space simplifies modelling. Gravitational forces decrease smoothly with distance, and light propagation remains predictable. There are no sudden changes in medium or structure that would complicate calculations at the scale of stars. As this idea settles, the image of space as a crowded expanse gives way to one of openness and separation. Stars exist as isolated centres of mass and light, each surrounded by a large region of near vacuum. Their distances from one another are a natural outcome of how matter is distributed. This perspective removes the need to imagine space as busy or congested. Even in the heart of a galaxy, space is calm and spacious. The distances between stars ensure that interactions are rare and gradual. With this understanding, the concept of distance becomes quieter. It is not something that presses or confines. It is simply the space that allows stars to exist independently, following long, predictable paths. The idea can rest here, grounded in scale and proportion. Emptiness is not absence, but the normal condition between stars. Distance is the expression of that condition. In some regions of the galaxy, stars are found closer together than average, forming groups known as star clusters and stellar associations. These regions provide a useful contrast to the more typical spacing found elsewhere, because they show how distance between stars can vary, while still remaining large by everyday standards. Even here, separation dominates over closeness. Star clusters form when large clouds of gas collapse and fragment, creating many stars within the same general region. Because these stars share a common origin, their initial distances from one another are smaller than those of stars formed in isolation. Yet smaller, in this context, still means distances measured in fractions of a light year or more. Stars are not packed side by side. Each one occupies its own volume of space. There are two broad types of clusters: Open clusters contain hundreds to a few thousand stars and are typically found within the disk of the galaxy. Their stars are loosely bound and gradually drift apart over time. Globular clusters contain many more stars and are more tightly bound, but even in these dense environments, the space between stars remains vast compared to stellar size. In an open cluster, the average distance between neighbouring stars may be a fraction of a light year rather than several light years. This is closer than average, but still far enough that direct interactions are rare. Over millions of years, gravitational effects and the influence of the surrounding galaxy slowly disperse these clusters, increasing the distances between their stars. Globular clusters present a different pattern. They're older and more stable, containing stars packed into a roughly spherical volume. Near the centre of a globular cluster, stars are closer together than anywhere else in the galaxy. Even so, the typical separation remains large enough that collisions are uncommon. Space between stars continues to dominate. These clusters illustrate an important principle. Higher density does not eliminate distance. It simply reduces it within limits set by gravity and motion. Stars still require space to maintain stable orbits and to evolve without constant disruption. Stellar associations, which are even looser groupings, show how stars can share a region of space without being tightly bound. These stars move in similar directions for a time, gradually spreading out as they orbit the galaxy. Their distances increase smoothly, blending into the surrounding stellar population. From an observational standpoint, clusters can appear crowded because many stars lie in similar directions and at similar distances. This visual density does not imply physical contact. It reflects alignment and shared origin rather than compression. Studying clusters helps astronomers understand how distance evolves. By observing how clusters change over time, scientists can track how stars drift apart, how gravity reshapes spacing, and how distance increases naturally as systems age. As this idea settles, clusters can be seen as temporary variations within a broader pattern. They do not contradict the general sparsity of space, they refine it. They show that distance between stars is flexible within certain bounds, shaped by formation and motion. Even in these closer environments, space remains calm and open. Stars continue to exist as individual systems, separated by regions of emptiness that preserve stability. Distance remains the defining feature, even where stars gather. This understanding prepares the way to consider how distance changes over time. As stars move and the galaxy evolves, without disrupting the steady framework already in place. The distances between stars are not fixed forever. While they remain stable over human timescales, they change gradually over much longer periods as stars move through the galaxy. Each star follows its own orbit around the galactic centre, guided by gravity and influenced by the overall mass of the Milky Way. These motions are slow and steady, but over millions of years they alter how far stars are from one another. Stars do not travel together as a rigid structure. Even stars that formed in the same region begin to drift apart once the gas that bound them disperses. Small differences in speed and direction accumulate over time, increasing the distance between neighbouring stars. This process is gradual and continuous, without sudden changes. The typical speed of a star orbiting the galaxy is on the order of hundreds of kilometers per second. While this may sound fast, the distances involved are so large that noticeable changes in separation require very long durations. Over a lifetime, the relative positions of nearby stars shift only slightly. Over tens of millions of years, patterns slowly rearrange. This motion explains why star clusters disperse and why stellar neighbourhoods evolve. A region that once contained many stars close together may become more spread out, blending into the general background of the galaxy. Distance increases naturally as motion continues, following predictable paths. Despite this motion, stars rarely approach one another closely. The vast spaces between them act as buffers. Gravitational encounters that significantly alter orbits are uncommon outside dense clusters. Most stars pass through the galaxy without close interactions, maintaining wide separations. From a measurement perspective, stellar motion adds a time component to distance. Astronomers can track how a star's position changes across the sky, and how its distance slowly varies. These measurements provide insight into galactic dynamics without altering the basic framework of distance. This slow change reinforces a sense of continuity. Space does not rearrange itself abruptly. Distances evolve gently, shaped by motion that is consistent and well understood. The structure remains calm even as it shifts. As this idea settles, distance can be understood not as a static property, but as one that adjusts smoothly over time. The same physical rules apply at every moment. Stars move, space remains open, and separation persists. The concept rests here, steady and unhurried, allowing motion to exist without urgency, and distance to remain a stable guide. Distance plays a direct role in what can be observed and measured about a star. The farther a star is from Earth, the more its light spreads before reaching us, and the less detailed the information becomes. This effect is not sudden. It increases gradually with distance, following clear physical rules that apply uniformly across space. As distance increases, a star appears dimmer, even if its intrinsic brightness remains unchanged. This dimming is a simple consequence of light spreading over a larger area. The same amount of light energy is distributed across more space, reducing the intensity that reaches any single point. This relationship allows astronomers to connect observed brightness with distance once the star's true luminosity is known. Distance also affects resolution. Nearby stars can be studied in greater detail. Their spectra can be measured precisely, revealing temperature, composition, and motion. For more distant stars, these measurements become less exact. Fine details blend together, not because they disappear, but because their signals weaken with distance. Despite this, distance does not erase information entirely. Even very distant stars carry identifiable signatures in their light. Spectral lines remain present, and patterns can still be recognized. Astronomers adapt their methods to match the scale, using longer observations and more sensitive instruments to recover detail. The effect of distance on observation reinforces the importance of measurement over appearance. A faint star is not assumed to be small or weak. It may simply be far away. Distance must be determined independently before physical conclusions are drawn. This separation between observation and interpretation keeps understanding stable. Distance also influences which stars dominate our view of the galaxy. Nearby stars are overrepresented in catalogues because they are easier to observe. Distant stars are numerous, but many remain unseen or unresolved. This observational bias is well understood and corrected for in scientific studies. By accounting for distance, astronomers can reconstruct a more accurate picture of stellar populations. They can estimate how many stars exist in regions beyond direct observation, and how those stars are distributed. Distance becomes a tool for correction rather than limitation. As this idea settles, observation feels less selective and more systematic. What is seen is shaped by distance, but not distorted by it. The rules remain consistent. Light weakens predictably. Detail fades gradually. Understanding this allows observation to remain calm and precise. Distance does not obscure truth. It simply sets the scale at which information arrives. To make sense of the distances between many stars at once, astronomers rely on mapping. These maps are not images in the usual sense, but structured representations built from measured positions and distances. Each star is placed according to direction and depth, creating a three-dimensional model of a region of space. This process transforms individual distance measurements into a coherent spatial structure. The foundation of these maps is consistency. Distances measured by parallax anchor nearby stars. Other distance indicators extend outward, calibrated against those anchors. When combined, they allow stars to be positioned relative to one another with known uncertainty. The map grows outwards smoothly, maintaining alignment between methods. Three-dimensional stellar maps reveal patterns that are not visible in the sky alone. Streams of stars moving together, regions of higher density, and gaps where few stars exist all become apparent. These features are not imposed. They emerge naturally once distance is included as a dimension. Mapping also clarifies motion. By measuring how stars move across the sky and how their distances change, astronomers can trace their paths through the galaxy. These motions are slow and orderly, reflecting long-term gravitational structure. Distance allows motion to be understood without ambiguity. Importantly, these maps do not require imagining the full galaxy at once. They are built incrementally, region by region. Each section is stable on its own, connected to others through shared reference points. This modular structure keeps understanding grounded. As this idea settles, distance becomes part of a quiet framework. Stars are no longer isolated points. They occupy positions within a mapped space separated by measured intervals. The galaxy takes shape as a calm arrangement of distances and directions, held together by steady motion and time. When attention moves beyond the boundaries of the Milky Way, distance takes on a slightly different character. While still obeying the same physical rules, stars in other galaxies are separated from us by distances so large that individual stars usually cannot be resolved. Instead, their light blends together, forming the soft glow of distant galaxies. The distance between stars still exists, but it becomes part of a larger pattern. Within another galaxy, stars are spaced in much the same way as they are in our own. The same processes of formation, motion, and gravity apply. The difference is that the entire system lies far beyond our immediate reach. The distances involved are measured not in light years, but in millions or billions of light years when considering separation between galaxies. Because individual stars in distant galaxies cannot usually be measured directly, astronomers rely on collective properties. The brightness of entire stellar populations, the behaviour of certain well-understood stars, and the motion of galaxies themselves all contribute to distance estimates. These methods extend the same principles used locally, without changing their foundation. This extension does not introduce a new kind of distance. It simply enlarges the scale. Light still travels at the same speed, brightness still follows the same laws, geometry still applies. The distances between stars within distant galaxies remain comparable to those within the Milky Way, even though the galaxies themselves are far apart. As this idea settles, distance across the universe feels continuous rather than segmented. Nearby stars, distant stars, and stars in other galaxies all belong to the same spatial framework. The numbers grow larger, but the structure remains familiar and stable. Distance and time are closely linked in astronomy because light does not arrive instantaneously. Every observation of a star is an observation delayed by the time light needs to cross space. This delay is not an added complexity. It is a natural feature of how information moves and is fully accounted for in measurement. When a star is observed at a distance of 100 light-years, the light being received left the star 100 years earlier. This does not mean the star is frozen in that past state. It means the information reaching Earth reflects the star as it was at that time. Distance defines how old the information is, not how far behind reality we are in understanding structure. This relationship remains linear and predictable. Each additional light year adds one additional year of light travel. There is no accumulation of uncertainty. The same speed applies everywhere. This consistency allows distance and time to be treated together without confusion. In practice, astronomers separate position from observation time. A star's current position is modelled based on its motion, while the observed light provides information about its past state. These two descriptions coexist without conflict. Distance governs the delay. Motion governs the change. This approach keeps understanding stable. There is no need to interpret distance as distortion or loss. It is simply a delay that can be calculated and corrected for when necessary. The structure of space remains intact. As this idea settles, distance becomes quietly temporal as well as spatial. Space extends outward, and light moves through it steadily. Observation follows naturally, arriving when it does, carrying information shaped only by time and distance. When distances between stars are considered across many regions and scales, certain patterns begin to appear. These patterns are not exact repetitions, but stable tendencies shaped by the same physical processes acting over long periods of time. Star formation, motion, and gravity leave consistent marks on how stars are spaced, regardless of location. One such pattern is the relationship between density and environment. Regions with more gas tend to form stars more frequently, leading to slightly smaller average distances between stars. Regions with less material form fewer stars, resulting in larger separations. This balance remains steady across the galaxy. The numbers change, but the relationship holds. Another pattern involves motion. Stars in similar regions tend to share similar orbital paths around the galactic center. This shared motion preserves spacing over long durations. Even as stars drift, their relative distances change slowly, maintaining broad structure rather than dissolving into randomness. These patterns extend beyond individual galaxies. Across different galaxies, stars are found to follow comparable spacing rules. Spiral galaxies show similar distributions within their disks. Elliptical galaxies show different arrangements, but still maintain large separations between stars. Distance behaves consistently, even when structure varies. Importantly, these patterns are descriptive, not intentional. They do not imply design or optimization. They arise naturally from gravity acting on matter over time. Distance becomes an outcome rather than a goal, shaped by processes that repeat wherever conditions are similar. As this idea settles, distance between stars can be understood as part of a larger regularity. It is not arbitrary. It reflects how matter organizes itself when given enough time and space. This regularity allows predictions without requiring exact knowledge of every star. The presence of pattern brings calm continuity. Distance is not an isolated fact for each star. It is part of a system that behaves in familiar ways, even across vast scales. This recognition allows attention to widen gently, without introducing abstraction or meaning. The structure remains physical, measurable, and stable. Within the broad pattern of stellar distances, the position of Earth and the Sun can be described without emphasis or interpretation. The Sun occupies a location in the disk of the Milky Way, at a distance from the galactic center that places it among many other stars with similar spacing and motion. The distances between the Sun and its neighbouring stars follow the same rules seen elsewhere in the galaxy. From this position, the surrounding stars form a local environment that is neither unusually dense nor unusually sparse. The Sun is not isolated, and it is not in a crowded region. The distances to nearby stars are typical for this part of the galaxy. This normality is useful because it allows local measurements to represent broader patterns. Human observation begins from this location, but the physics involved does not depend on it. Distances between stars would remain the same if observed from elsewhere. Measurement methods are designed to remove observer bias, placing stars in a shared coordinate system rather than centering them on Earth. This perspective keeps the discussion grounded. The Sun is one star among many, separated from others by measurable distances that reflect common galactic structure. Nothing special is required to explain its placement. As this idea settles, attention rests briefly on location without attaching importance. Position is simply where observation happens to begin, not a defining feature of space itself. After moving outward through larger and larger scales, it is natural to let attention return gently to the stars visible from Earth. These stars, scattered across the sky, represent many different distances layered along each line of sight. Some are relatively nearby, others are much farther away. Together they form the familiar night sky. Seen with this understanding, the sky does not change its appearance. Stars remain points of light. What changes is the quiet knowledge that depth extends behind each point. Distance becomes an accepted background property rather than an active focus. This return does not compress scale or undo what has been learned. The larger framework remains present, but it no longer demands attention. Distances exist whether they are considered or not. The sky can simply be observed again. This settling allows understanding to rest without conclusion. The structure of space holds steady, extending outward even when attention narrows. The distance between stars is a continuous feature of space shaped by formation, motion, and time. It does not require interpretation or response. It simply exists, measured through light and geometry, stable across long spans of time. Stars remain separated by wide regions of emptiness, forming patterns that change slowly and predictably. These distances do not rush or collapse. They persist, allowing structure to endure. There is nothing further to resolve. Space extends, light travels, measurement holds, everything flows. Sleep in that motion.